Hi Year 10, welcome back to part 2 of the computational thinking module that represents 50% of our GCSE. Last week we did merge sort algorithm, bubble sort algorithm, insertion sort algorithm. We learned about big O notation and how fast these algorithms are. And we found that the merge sort was a much faster algorithm to use. Now, this video today, we're going to be doing searching algorithms, and searching algorithms are nice and simple to do. So it's a short video today, not as long as as part 1. Okay, so let's get on into it. So the linear search algorithm, this is like the easiest algorithm I will ever teach you. It literally is nice and simple. Now, before we start, a searching algorithm is basically finding an item of data. This could be a letter, it could be a number. It's basically finding something. If it finds something, it returns the index value of where it is. Now, with index values, don't forget they're in arrays and lists. So, for instance, they always start at 0 in computer science and move on up. So this question says, show the stages of the linear search algorithm when finding the letter D in the sequence. So let's have a look at the sequence. Here it is. And here's the index values. It's really important that you note these index values. Literally just start on 0, count all the way up. So here's our items, and we are finding D. So a nice, simple algorithm for this is the linear search. It is as simple as A is not equal to D, F is not equal to D, B is not equal to D, E is not equal to D. Oh, D is equal to D. We've found it. Return 4, because that's the index value of where D is. So it's nice and easy, nice to use, and you just literally write the steps down one by one, and you start from the left side and you work all the way up till you found it. If you haven't found it, no worries. You'd just go all the way through the entire list or array, and then if you haven't found it, you just say not found. How you would write an answer to this is this, just there. So it says like A is not equal to D. You can write the not equal to symbol. It's basically like 2 equal signs with a line through. A line through like that means not equal to in computer science. So can you please just write down that little table there, linear search is the title, write down the whole slide, and then that's enough notes for the linear search algorithm. So pause the video and then write down the notes. Okay, guys, so I've got a question for you using the linear search algorithm. Can you please find the number 8 in the sequence 7, 5, 2, 8, 5, 3? Can you write it down like it's an exam answer? Pause the video, come back, and we'll go over the answers. All right, guys, so the answer literally is going through. So 7 is not equal to 8, 5 is not equal to 8, 2 is not equal to 8, 8 is equal to 8, found, return 3, because the index value of where 8 is 3. The most easiest algorithm, guys. You don't need to worry about whether it's in order, whether it's what items you have in the array. You just literally search through like that. So just remember that for when an exam question comes up, because it's a nice couple of easy marks for you. Okay, so the next one is the binary search algorithm. Now, this is quite a toughie, and you've got to think about each step as you go. It can be quite difficult at times. The first rule of the binary search algorithm, and this is so important, is that it has to be in order. If it's not in order, this algorithm does not work. Sometimes the exam board has caught people out in the past, and they say like, why can't we do this algorithm? And your answer will always be because it's not in order. So you can only search for the binary search algorithm if it is in order. Has to be in order. In order. In order. All right. Remember that. In order. Has to be in order. Has to be in order. All right. So we've got this question here. We've got an array of numbers. They're all in order, so they're already sorted for us. Sometimes it'd be great. I mean, I hope the day comes up when you get asked to do like a insertion sort algorithm on an array of numbers, and then the question's followed by this binary search algorithm. It would just be about 10 marks, 10%, not 10% of the paper. Nice and easy. More than 10% of the paper. So it's all about, it's in order, and it's about finding midpoints. Now, the rule for finding the midpoint is the upper bound, which here we have 10. And the lower bound, which we have 0. So we look at the index values, okay? So then all you do is just do the upper bound added to the lower bound, divided by 2. So we've got 10, the upper bound index, plus 0 index, divided by 2 equals 5. So our midpoint in this is position 5 or index 5. So then what we do is we have a look at index 5 and we go, okay, we've got 16. Now, this isn't equal to 19 because we're trying to find the number 19. So you now know that 19 is not going to be in 14, in index 4. It's not going to be in 3. It's not going to be in 2. It's not going to be in 1. Why? Because 16 is less than 19. And the whole array is in order, so we can just delete that half of the array. So we can remove index 5 and anything below it because we know it's not there. There we go. So it's removed. So now we're left with this. Now we need to find our next midpoint. So we look, we've got index 6 as our lower bound. We've got index 10 as our upper bound. 6 plus 10 is 16. Divide that by 2. So therefore our midpoint is 8. So we look at position 8 and we go, right, we've got 40. We're trying to find the number 19. Well, 19 is a lot less than 40. So 40 is bigger than 19. So we know we can delete index 8 all the way on forward, 75, 80, index 9, index 10, because it's in order. So we don't have to worry about it. So we can delete all of that lot and search through the rest of the array. So remove indexes 8, 9, and 10, like that. And now we're just left with indexes 6 and 7. So now we're left with these. We now need to find our next midpoint, even though it's quite clearly obvious for a human, but this is how the algorithm actually goes. So we need to keep on following the same steps, finite sequence of instructions in order to solve a problem. All right, so 6 plus 7 is 13. Divide that by 2 is 6.5. We've got a problem. We've got a decimal point. We can't cut it in half evenly. The rule here, our next really important rule to remember is with binary search, you round up. Yeah, round up. I'm not swearing. So yeah, round up. Please do round up with binary search, guys. So we've got a midpoint. It is 7. So we look at index 7 and we go, right, okay, is 25 equal to 19? No, it's not. 25 is greater than 19. So we know we can remove index 7 and anything beyond that, if there is anything beyond that. Here there isn't. So we can remove index 7. So goodbye, index 7. And now we're just left with the bottom index just here, which is index 6. So again, the algorithm will try and find a midpoint, even though it's quite clear there's only one left. So here the midpoint is 6 because the lower bound is 6. The upper bound is also 6. So 6 plus 6 is 12. Divide that by 2, it's 6. And then we just check to see if 19 is equal to 19. Here, 19 is equal to 19. We have found the number 19. So we return 6. We return the index value on where we found it. So there we go. So guys, it's quite tricky remembering steps. Just remember the two rules. Midpoint is equal to lower bound plus upper bound divided by 2. You round up when you've got a decimal for your midpoint. And anything beyond that is literally just, is it higher than, is it lower than? If it's higher than, you remove everything to the index you check in and everything to the right. If it's less than, you remove everything you check in and it remove everything to the left. And it's literally, this is called, I was talking about this in part 1, a dynamic algorithm. Now, a dynamic algorithm is divide and conquer. So you're consistently cutting your problem in half each time. And this is super fast. It's n log n, like the merge sort. So it's super fast. So for instance, if you've got like, I don't know, 100 numbers, with the linear search, it's big O n. So if you've got an array that's got 100 items in it, we don't know what items are in it. And if the item you're searching for is right at the end of the array, so at index 99, you know that the linear search algorithm is going to do 100 comparisons before it actually stops and executes. This is big O to the n because we've got 100 items in the array and it's right at the end. It's going to take forever. Well, until the end of the array if it's in there. Now, it's super quick though, the linear search as well, because if your item's right at the start of the array, so like you've got a million items now, and your item's right at the start that you're looking for with a linear search, you're only going to do one comparison, which is going to make it like super quick, which is awesome. But on average, with a linear search, it's always half the size of your array. So if you've got 10 numbers, on average, it's going to take 5 comparisons before it finds it. So yeah, it depends on where the item is in that array. Sometimes that's a question that could come up, which you need to explain why the linear search could also be fast, but it also could be slow. So it's fast when it's at the start of the array, it's slow when it's at the end of the array. With this binary search, it's fast all the time because it's consistently cutting its problem in half each time. So for instance, imagine you've got an array of 100 again. By the first comparison, you've removed 50 of them. Then by the next comparison, you've removed another half of that, half of that, half of that, and so on. So yeah, it's much, much quicker. Right, it's time for some notes. So can you guys please copy down all of this slide just here? I would like the 2 rules written down as well. So say like the lower bound plus the upper bound divided by 2 is equal to the midpoint. And the second rule, which is always round up on a midpoint. And we'll practice some questions with the binary search. All right, guys, so pause the video, get that down, and then come back. Okay, then, guys, welcome back. I've got your first question just here. Can you please conduct a binary search on that array to find the number 2 in the array? So pause the video, answer the question, and then come back. All right, guys, welcome back. I hope you got my trick question. You cannot do a binary search on this array because it's not in order. So therefore, all you would write here is that you can't do a binary search on this as it's not in order. However, you need to look at the marks for the question. If the marks say are like 10 marks, then just put it in order and put a comment at the top saying that you're putting it in order because you can't do a binary search without putting it in order. If you put it in order, fair play. But I hope you've written down a comment saying that you can't do a binary search without it being in order. So a bit of a trick question for you there, guys. I'm sorry. All right, so question 2. Okay, guys, question 2. Can you please conduct a binary search on this array to find the number 24? It's in order this time, so you should be able to do it. All right, so pause the video, answer the question, then come back. Okay, and guys, welcome back. I hope you found that okay. You just got to remember those steps. So we're going to go through the answer here. So we've got what I like to do is to start with, I like to put my index values down. So 0, 1, 2, 3, 4, 5, 6, 7. Now we need to find a midpoint. So I'm just going to put M here as I'm in Paint. So midpoint is equal to the lower bound, which is 0, plus the upper bound, which is 7, divided by 2, which is equal to 3.5. And we round up, so it's equal to 4. So then we look at 4 and we say, well, 22 is less than 24. So what we can do is we remove all of this side just here. So let's rewrite out our array. So let's write a little comment in here actually to start with. Let's say remove index 4 and below. And let's rewrite out our array now. So we have left 24, 56, and 78. Now, the index values never change. So once you've cut it in half and stuff, it still never changes. So our index here is still 5. Our index here is still 6. And our index here is still 7. All right, so now again, we find the midpoint. So the midpoint is 5, which is our lower bound, plus 7, which is our upper bound, which is equal to 12. Well, let's do divide by 2, which is equal to 12. And then divide that by 2. We've got a midpoint of 6. Now we look at 6 and we say, well, 56 is greater than 24. So what do we do? Index 6 and below and above. And we remove index 6 and above. Okay, so our array just has one number in now, and that's 24. And it is index 5. So we have our lower bound is 5. Our upper bound is 5. Divide that by 2. So 5 plus 5 is 10. Divided by 2, which is 5. So here we say 24 is equal to, I've done 2 equals because it means directly equal to, 24. So we return 5. All right, guys, I hope that was okay. I'm now going to give you an exam question from OCR. So the question reads, a second sample of data is shown in figure 4. So we've got amber, house, kick, moose, orange, range, tent, wind, zebra. Show the stages of a binary search to find the word zebra when applied to the data shown in figure 4. So this is 4 marks, guys. So give that a shot. It looks to me like it's alphabetical order. Just treat it like you would with numbers. All right, folks. So pause the video, answer that question, and then come back. Okay, guys, welcome back. So let's look at the answer, and you get a mark per correct bullet point here. So at the start, if you found that midpoint of orange and you compared zebra to orange, you get a mark. If you removed the right side, you get another mark. Here, you get another mark if you've done a further comparison on comparing wind to zebra. It says 1 or 2, depending on choices made here. Depends on how the algorithm's been coded, but we're following always round up. Correct identification of zebra using methodology above. So it says compare zebra to orange, greater split right, compare to wind, greater split right, compare to zebra, found it. So I hope you got those marks. If there's any trouble with the binary search or even the linear search, guys, just let me know. Can you please just write at the end of your binary search that the speed is n log n, big O n log n? And can you also write that the linear search is big O n? That's it for today's lesson, guys. I hope you found that okay. As per usual, drop me an email if you need anything. Thank you very much. Bye-bye.